In the grand tapestry of the cosmos, the presence of asteroids serves as a poignant reminder of our planet's fragile existence. These ancient celestial wanderers, remnants from the early solar system, traverse the void, embodying both danger and wonder. Imagine, if you will, a world, our world, hurtling through space, a fragile oasis suspended in a vast, indifferent universe. Asteroids, some the size of cities, others mere pebbles in the cosmic sea, present a paradox. They are both harbingers of potential catastrophe and intriguing messengers of our solar system's history. The impact of a significant asteroid could reshape life on Earth in an instant, just as it may have done in the distant past when the age of the dinosaurs came to an abrupt end. Yet, in the face of this cosmic threat, humanity's response is a testament to our intellect and ingenuity. Through observation, mathematics, and increasingly sophisticated technology, we seek to predict and, if necessary, mitigate the potential hazards posed by these celestial bodies. The work of astronomers and scientists, mapping trajectories, analyzing compositions, turns our gaze upward, connecting us to the universe in profound ways. Let us remember that we are not merely passive inhabitants of this blue planet. We are active participants in a grand cosmic narrative. The study of asteroids challenges us to confront our vulnerability and embrace our capacity for foresight and resilience. In the cosmic ballet, we dance on the edge of peril, ever curious, ever reaching for understanding, driven by the hope that knowledge can illuminate our path through the darkness of the unknown. As we peer into the abyss of space, we are reminded of our own insignificance, yet also of our profound potential. Asteroids, those rocky time capsules, contain the building blocks of our solar system, whispering secrets of its formation and evolution. They carry the elements that forged our planet and the very molecules that may have sparked the emergence of life itself. Consider, for a moment, the origins of these celestial wanderers. Formed in the fiery crucible of the early solar system, they are akin to frozen relics of a time long past. Each one bears the scars of cosmic encounters, an archive of impacts and interactions. In studying them, we not only unravel the mysteries of our own planet, but also ponder the fate of others in the solar system, and perhaps beyond. Yet, the potential hazards they present are real and pressing. While many asteroids languish in the vastness of the asteroid belt, others stray closer to Earth, tracing orbits that bring them into our neighborhood. The task before us is daunting yet vital: to track these wanderers, to anticipate their paths, and to devise strategies that might avert disaster should a threatening The story of humanity is one of triumph over adversity, of knowledge wrested from the jaws of ignorance. It is a narrative punctuated by moments of clarity, like the realization that we are not alone in this universe, nor are we immune to its forces. The efforts to safeguard our planet from asteroid impacts are not merely scientific endeavors. They are acts of stewardship, of guardianship over this fragile blue orb. In our quest for understanding, we confront our own limitations. The vastness of space reminds us of our smallness, yet it also calls forth our curiosity and courage. With each discovery, we are reminded that the universe is a dynamic, ever-changing place, where the past, present, and future are intricately woven together. As we continue to ponder the implications of asteroid hazards, we must recognize the profound responsibility that accompanies our quest for knowledge. With each discovery, we are not only unraveling the mysteries of the universe, but also grappling with the ethical considerations of our actions. The question arises: what should we do if we find ourselves facing a potential impact? To answer this question requires collaboration on a global scale. Nations must unite, setting aside their differences to focus on a shared vulnerability. In the spirit of scientific inquiry, we must create frameworks for communication and cooperation, pooling resources, expertise, and technology to build a comprehensive defense against these cosmic threats. The very act of coming together in the face of potential disaster is a testament to our humanity, a recognition that as we stand at this crossroads, let us embrace the duality of our existence. We are both fragile and resilient, vulnerable yet capable of great innovation. The asteroids that roam the solar system remind us of the impermanence of life and the power of knowledge. Each discovery invites us to marvel at the cosmos, to contemplate our origins, and to forge a future that honors our intercon. So, let us gaze upon the night sky with a sense of awe, knowing that each tiny speck of light holds the potential for both inspiration and peril. In our pursuit of understanding, may we harness our curiosity to build a brighter, safer future for all of humanity. A future where the wonders of the universe serve as a guiding star. In the infinite expanse of the cosmos, asteroids drift like ancient mariners, relics of the solar system's infancy. They are time capsules, each bearing the history of celestial creation and evolution, whispering tales of the forces that shaped not only their rugged surfaces, but also the very world we inhabit. Yet, amidst their beauty and intrigue lies an unsettling truth. These cosmic wanderers also harbor the potential to unleash catastrophic destruction upon our planet. Imagine a day when the skies darken and a streak of light appears. An asteroid, once an innocuous traveler, now on a collision course with Earth. The heart races at the thought of such a moment. For many, the specter of an asteroid impact conjures images of annihilation, reminiscent of the cataclysm that heralded the end of the dinosaurs. This is not mere science fiction. It is a profound reality we must confront. The asteroid belt, a vast region between Mars and Jupiter, is home to countless rocky bodies, remnants from the birth of our solar system. While most of these asteroids pose little threat, a small fraction near-Earth objects occasionally stray from their orbits, entering our cosmic neighborhood. They serve as a reminder of our vulnerability in this delicate cosmic dance. Yet, with knowledge comes power, and humanity's understanding of these celestial bodies is evolving. Asteroid detection and tracking have become paramount in our quest for safety. Observatories equipped with advanced telescopes scan the heavens, mapping the trajectories of these wandering rocks. The technological marvels we develop in this pursuit are not only critical for planetary defense but also illuminate our understanding of the solar system. We discover that these objects can be composed of metals, ice, or even organic materials, hinting at the very origins of life. The prospect of deflecting a threatening asteroid has ignited the imaginations of scientists and engineers alike. Concepts once relegated to the realm of science fiction are now within reach. Kinetic impactors, gravity tractors, and even nuclear options have been proposed as potential solutions. However, these endeavors require not only scientific rigor but also international collaboration. We must recognize that the fate of our planet transcends borders, uniting us in a shared responsibility to protect our home. Yet, in our fervent quest for solutions, we must not overlook the philosophical implications of our journey. What does it mean to exist in a universe where cosmic hazards loom overhead? It calls for a deeper reflection on our place within this grand tapestry. We are not isolated entities, but part of an intricate web of life, all influenced by the forces of the cosmos. The very act of contemplating asteroid hazards can inspire a renewed sense of stewardship for our planet and its ecosystems. Furthermore, our interactions with asteroids can yield unexpected benefits. The resources they contain, metals, water, and organic compounds, offer tantalizing possibilities for future space exploration. Imagine a future where humanity extends its reach to the stars, utilizing asteroids as stepping stones for colonization and scientific inquiry. In this vision, the very threats we face could become instruments of our survival and advancement. As we reflect on these celestial bodies, we must embrace the duality of their nature. They are both symbols of peril and harbingers of opportunity. The knowledge we gain about asteroids not only enhances our preparedness, but also enriches our understanding of the cosmos. Each discovery sparks a sense of wonder, urging us to look beyond the horizon, to explore, to question. So, let us not succumb to fear, but rather approach the asteroid hazard with curiosity and resolve. In the vastness of space, we are a small yet significant part of a grand narrative, a narrative where knowledge is our guiding light. Let us strive to unravel the mysteries of the universe, ensuring that we are not mere spectators of our fate, but active participants in shaping our destiny. The cosmos beckons, and as we venture forth, may we do so with wisdom, unity, and an unwavering sense of hope. As we continue to delve into the complex relationship between humanity and the asteroids that traverse our solar system, we must acknowledge the lessons they impart. They remind us that, in the grand cosmic scheme, we are but fleeting sparks of consciousness, capable of great achievement yet susceptible to forces far beyond our control. The vastness of space is not merely a backdrop FO. Consider the profound significance of an asteroid impact. Such an event could alter the trajectory of life on Earth, triggering environmental upheaval and reshaping ecosystems. The legacy of past impacts is etched in our planet's geological history. These cataclysmic events serve as a stark reminder of nature's power and unpredictability. Yet, they also reveal a remarkable resilience life has. In the face of potential disaster, we are challenged to rise to our better selves. The global response to asteroid hazards could inspire a new era of collaboration and innovation. Imagine a world where scientists, engineers, policymakers, and citizens unite, pooling their knowledge and resources to devise effective strategies for planetary defense. This collective effort could foster a sense of shared purpose, transcending political and cultural boundaries. It offers an opportunity to demonstrate the best of humanity. The pursuit of asteroid research also serves to ignite our curiosity about the cosmos. Every mission to explore these celestial bodies enriches our understanding of the solar system's formation and evolution. The very act of venturing into space, of sending probes to rendezvous with asteroids, reaffirms our commitment to exploration and discovery. It encourages us to ask questions. How did the solar system form? Are we alone in the universe? What other mysteries lie be? Moreover, the technology we develop to study and mitigate asteroid threats has profound implications for life on Earth. The same techniques used to track and deflect asteroids can enhance our capabilities in other fields, such as disaster response, climate modeling, and environmental monitoring. The quest for planetary defense could catalyze a renaissance in scientific research, fostering innovations that benefit humanity in ways we may not yet fully. As we further contemplate the implications of asteroid hazards, we uncover a rich tapestry of connections that weave together science, philosophy, and our collective future. These celestial bodies are not merely threats to our existence. They are, in many ways, mirrors reflecting our own aspirations and fears. They challenge us to confront the limits of our knowledge while simultaneously. The prospect of an asteroid impact compels us to confront the fragility of our civilization. It forces us to consider how we prepare for the unexpected, to acknowledge that despite our technological advancements, we remain vulnerable to the whims of the cosmos. Yet, it is precisely this vulnerability that can inspire resilience. History has shown us that humanity often rises to the occasion, finding strength in unity and ingenuity. In the face of adversity, we have demonstrated a remar. We stand at a pivotal moment in our journey as a species. Our understanding of asteroids has evolved from mere curiosity to a proactive approach in planetary defense. The advent of space missions designed to study and even redirect asteroids heralds a new era of exploration. Missions like NASA's DART, Double Asteroid Redirection Test, represent a bold step forward, testing our capacity to alter the course of a celestial body. But beyond the mechanics of deflection lies a deeper philosophical question. What does it mean to intervene in the natural order of the universe? As we contemplate our role as stewards of Earth, we must also consider the implications of our actions. The pursuit of asteroid defense challenges us to reflect on our relationship with the cosmos and our responsibilities toward it. Are we mere inhabitants of this planet, or are? In this light, our engagement with asteroids can serve as a catalyst for broader conversations about sustainability and environmental stewardship. The knowledge we gain from studying these objects can inform our understanding of Earth's own geological history, helping us to appreciate the delicate balance of ecosystems and the impacts of our actions. As we explore the cosmos, we must also nurture our home, recognizing that the LESO, NASA's Double Asteroid Redirection Test, DART, mission stands as a pioneering effort in planetary defense, marking a significant milestone in humanity's ability to respond to potential asteroid threats. Launched in November 2021, DART's primary objective was to demonstrate that a spacecraft could autonomously collide with an asteroid and alter its trajectory, a concept often referred to. The target of DART was the binary asteroid system known as Didymos, which consists of a larger asteroid, Didymos, and its smaller companion, Dimorphos. The mission aimed to crash the DART spacecraft into Dimorphos at a speed of approximately 14,000 miles per hour, 22,500 kilometers per hour. This impact was designed to change Dimorphos's orbit around Didymos, allowing scientists to measure the extent of that change and evaluate the effectiveness of this. The significance of DART extends beyond the immediate goal of deflecting an asteroid. It serves as a proof of concept for future planetary defense strategies, demonstrating that we have the capability to alter the course of potentially hazardous objects. In a universe where the threat of asteroid impacts looms large, DART represents a proactive step toward safeguard. As the spacecraft approached its target, it utilized advanced guidance systems and autonomous navigation to ensure a precise impact. The mission also relied on ground-based telescopes to monitor the results, with observations designed to capture any changes in Dimorphos's orbital path. This collaborative effort underscored the importance of international cooperation in planetary defense, as DART not only enhances our understanding of asteroid dynamics but also raises important questions about the future of planetary defense. The success of this mission could pave the way for more sophisticated deflection strategies, particularly as we refine our techniques for identifying and tracking near-Earth objects. Moreover, the insights gained from DART may inform our broader understanding. NASA's DART mission is a landmark initiative that encapsulates the confluence of scientific ingenuity, exploration, and the urgent need for planetary defense. As we delve deeper into the mission's implications, we can appreciate the broader context in which it operates. The DART spacecraft was ingeniously designed to operate autonomously. Equipped with sophisticated cameras and onboard navigation systems, it was capable of recognizing its target, Dimorphos, in the final moments before impact. This autonomous capability is a crucial aspect of the mission, demonstrating that we can rely on advanced technology to execute precise maneuvers in the unpredictable. Upon impact, the kinetic energy released was expected to create a measurable change in Dimorphos's orbit around Didymos. This data would provide invaluable insights into how effective kinetic impactors could be in future scenarios, where rapid response MIG. After the collision, the scientific community shifted its focus to monitoring and analyzing the effects of the impact. Ground-based telescopes and space observatories were mobilized to observe changes in the orbital period of Dimorphos. By measuring the time it took for Dimorphos to complete its orbit around Didymos before and after the impact, scientists could quantify the efficacy of the deflection strategy. This collaborative effort was a testament to the global nature of space science. Astronomers across continents worked together to track the aftermath, underscoring the importance of international cooperation in addressing shared challenges. Continuing our exploration of NASA's DART mission, it's essential to consider its broader significance in the context of planetary defense, scientific discovery, and international collaboration. At its core, DART was designed to test the feasibility of a kinetic impactor as a method for asteroid deflection. The choice of Dimorphos, a smaller body orbiting the larger Didymos, was strategic. This binary system allows for precise measurement of any changes in Dimorphos's orbit following the impact, as scientists can monitor the shift using telescopes both on Earth and in space. The physics involved is fascinating. When DART collided with Dimorphos, it transferred kinetic energy to the asteroid. The resulting change in velocity, although minuscule, could be enough to alter Dimorphos's orbit over time. This experiment not only validates a potential defense strategy but also deepens our understanding of the physical characteristics and behavior of asteroids, including their composition, structure, and the dynamics of impacts. Following the impact, the data collected will be crucial for refining models of asteroid behavior. Observations are expected to yield information about the material properties of Dimorphos, such as its density and strength. This information can inform not only future asteroid missions, but also our understanding of the formation of celestial bodies in the solar system. Additionally, the ability to measure changes in the orbital dynamics of asteroids provides a framework for predicting the outcomes of future encounters with potentially hazardous objects. This predictive capability is essential for assessing risks and determining appropriate response strategies. DART is just the beginning. The mission is expected to inspire a series of follow-up missions and initiatives focused on planetary defense. For instance, the European Space Agency is planning its own mission, Hera, aimed at characterizing the aftermath of the DART impact. Hera will study dimorphos and its interaction with didymos, providing a comprehensive assessment of the collision's effects and advancing our understanding of asteroid dynamics. These collaborative efforts represent a shift toward a more proactive approach in space exploration. They highlight the importance of partnerships between different space agencies and countries in addressing shared challenges, emphasizing that the risks posed by asteroids are a global concern. Beyond its scientific achievements, DART raises important societal questions about how we approach the concept of planetary defense. The idea of deliberately altering the trajectory of an asteroid may evoke a sense of unease. It compels us to engage in discussions about the ethical implications of such actions. How do we prioritize resources for planetary defense compared to other pressing global issues? What frameworks should guide our decision-making processes in these scenarios? These questions extend to how we communicate with the public about asteroid hazards. Educating communities about the science behind DART and the potential risks of asteroid impacts is vital for fostering understanding and cooperation. This outreach can help demystify the technology and inspire a sense of collective responsibility for planetary safety. The DART mission encourages us to think about the broader implications of cosmic risk. While asteroids are a tangible threat, they represent just one of many challenges we face as a species. Climate change, pandemics, and other existential threats also demand our attention and proactive responses. The spirit of collaboration and innovation demonstrated by DART can serve as a model for how we might address these issues collectively. In this way, the mission reinforces the notion that humanity is capable of rising to the occasion. It encourages us to view our existence as part of a larger narrative, one where we not only explore the cosmos but also take responsibility for our survival. In sum, NASA's DART mission is a groundbreaking endeavor that transcends its immediate goals. It stands as a testament to human ingenuity, collaboration, and the desire to protect our planet. As we await the results and insights from this mission, we are reminded of the profound interconnectedness of our existence. Each step we take toward understanding and mitigating asteroid hazards brings us closer to a future where we can navigate the cosmos with confidence, curiosity, and a commitment to safeguarding our world. The DART mission is not just a technical achievement. It is a symbol of our potential to confront challenges head-on and to embrace the vast unknown with hope and determination. Carl Sagan often spoke about the risks posed by asteroids and other celestial threats in the context of humanity's vulnerability and the need for scientific understanding. He emphasized that Earth is not immune to cosmic events, and that the potential for an asteroid impact represents a significant existential risk. Sagan highlighted the importance of studying these celestial bodies, not only to understand their origins and characteristics, but also to prepare for potential threats. He advocated for increased investment in space research and planetary defense, arguing that our survival may depend on our ability to predict and respond to such hazards. In his famous series Cosmos, Sagan explored the idea that our planet is a fragile oasis in a vast universe filled with dangers. He urged humanity to embrace a sense of responsibility for our future and to use our intelligence and technology to safeguard our existence. Overall, Sagan's perspective on asteroid hazards was a blend of scientific curiosity, caution, and a call to action, emphasizing the need for awareness and preparedness in the face of cosmic risks. While Carl Sagan did not specifically address NASA's DART mission, since it was launched long after his time, his insights and principles about asteroid hazards align closely with the mission's goals and spirit. Sagan advocated for the necessity of understanding cosmic threats like asteroids, emphasizing that knowledge is our best defense. He would likely have supported DART's objective of testing a kinetic impactor technique to alter an asteroid's trajectory, viewing it as a critical step in planetary defense. Sagan often spoke about the importance of space exploration for humanity's survival and advancement. He believed that investigating asteroids could yield valuable information about the early solar system and the origins of life. The DART mission reflects this ethos by not only seeking to protect Earth, but also expanding our understanding of celestial bodies. Sagan emphasized that addressing global threats requires international cooperation. He would likely see DART as part of a broader movement toward collaborative planetary defense, where nations work together to protect the Earth from cosmic hazards. Sagan's reflections on Earth's vulnerability would resonate with the goals of the DART mission. He often reminded us of the thin veil of life on our planet, highlighting the need for proactive measures to ensure its safety. DART embodies this proactive spirit by testing methods to prevent potential asteroid impacts. Finally, Sagan would likely appreciate DART as an example of humanity's capacity to innovate in the face of danger. He championed a sense of responsibility to future generations, urging us to take action not just for ourselves but for those who will come after us. The DART mission serves as a testament to that legacy of curiosity and commitment to planetary protection. In essence, while Sagan did not directly comment on DART, his ideas about asteroid hazards, scientific inquiry, and global responsibility resonate profoundly with the mission's objectives and values. Now we will talk about the influence of the magnetic field on the spectra of stars. In the grand ballet of the cosmos, stars shine like brilliant jewels scattered across the velvet backdrop of space. To the naked eye, they appear as simple points of light, twinkling from vast distances. But within that light lies a profound story. A star's spectrum, the rainbow of colors split from its light, is a cosmic fingerprint, revealing secrets about its temperature, composition, and motion. However, there is another force at play, an invisible hand that can subtly alter the spectrum, a force as ancient as the stars themselves, the magnetic field. Every star, like our own sun, is a cauldron of nuclear fusion, churning with immense energy. Deep within its core, hydrogen atoms collide and fuse, releasing light and heat that makes its way to the surface and then out into space. But this stellar furnace does not operate in isolation. It is enveloped in a magnetic field, a powerful, unseen force that weaves through the star's interior and reaches out into space, shaping and guiding the very light that escapes from its surface. Magnetic fields influence stars in ways both subtle and profound. They twist and stretch the plasma within the star, creating phenomena such as sunspots, cooler, darker regions on the star's surface where magnetic forces have suppressed the flow of heat. More significantly, these magnetic fields interact with the light itself, altering the star's spectrum in a way that astronomers have come to recognize. Imagine the light from a star traveling across the vast expanse of space toward Earth. As it moves, this light carries within it information, encoded in the form of wavelengths, each one corresponding to different elements that exist within the star. These wavelengths create lines in the spectrum, like the notes of a cosmic symphony. However, when a magnetic field is present, it disrupts this delicate music. The lines in the star spectrum, which would normally be sharp and precise, are split or broadened, a phenomenon known as the Zeeman effect. The Zeeman effect, first discovered in the late 19th century, is a direct consequence of the magnetic field interacting with the electrons within atoms. As the magnetic field tugs at the particles inside the star, it changes the way they absorb and emit light. What was once a single spectral line is now split into multiple components, each slightly shifted in wavelength. This subtle alteration is like hearing the same musical note played on different instruments, still recognizable, but transformed by the medium through which it travels. Through the careful study of these split lines, astronomers can measure the strength and orientation of a star's magnetic field. It is as though the spectrum of the star has become a language, one that speaks not just of the star's temperature or its chemical makeup, but of the invisible forces shaping its life. These magnetic fields are more than just curiosities. They play a critical role in the behavior and evolution of stars. In stars more massive than our Sun, magnetic fields can be even more intense, sometimes locking into complex structures that cause entire regions of the star's surface to behave unpredictably. The magnetars, a class of neutron stars, are the most extreme example. These stellar remnants have magnetic fields so powerful they warp space-time around them, bending light and matter in ways that challenge our understanding of physics. The spectra of these stars are distorted beyond recognition, their light flickering and fluctuating as the magnetic field twists and contorts the star's very essence. Even in more ordinary stars, like our Sun, magnetic fields shape their fates. They generate stellar winds, streams of charged particles that flow out into space, carrying with them pieces of the star's atmosphere. Over time, these winds can erode planets and alter the environments of entire solar systems. The magnetic field of a star, though invisible, extends far beyond its surface, interacting with the cosmic neighborhood in profound and sometimes destructive ways. And yet, these magnetic forces are also life-giving. On Earth, our planet's magnetic field shields us from the solar wind, creating the auroras that dance at the poles. Without it, the solar wind would strip away our atmosphere, leaving our world as barren as Mars. Similarly, on distant planets orbiting other stars, magnetic fields may offer protection from stellar winds, creating safe havens where life might flourish. As we peer deeper into the cosmos, studying the spectra of stars light-years away, we are not merely observing distant points of light. We are witnessing the intricate interplay between matter and energy, between light and magnetism. Each star's spectrum is a map of the forces that shape its life, from the nuclear fires at its core to the invisible magnetic fields that swirl around it. The story of magnetic fields and starlight is a reminder that the universe is not static. It is dynamic, alive with energy, and full of hidden forces that shape the cosmos in ways both seen and unseen. Every time we gaze at a star, we are, in a sense, witnessing the effects of these invisible fields, as they bend, twist, and transform the light that reaches our eyes. In this way, the stars become more than mere points of light in the night sky. They are cosmic storytellers, revealing to us not just their past and present, but the powerful unseen forces that will shape their futures. And as we continue to explore the universe, we will forever be drawn to the spectra of stars, knowing that within those lines lie the secrets of magnetism, light, and the eternal dance of the cosmos. The influence of magnetic fields on the spectra of stars is a story of deep cosmic interplay, a story that stretches across light-years, from the very core of a star to the farthest reaches of space. It is a tale of forces that are both invisible and yet omnipresent, shaping the very light that has traveled across the cosmos to reach our instruments, and with it, revealing some of the universe's most profound secrets. When we observe the night sky, we see stars as distant, twinkling lights. But each star, no matter how far away, is a vast furnace of nuclear reactions, endlessly transforming hydrogen into helium, generating immense energy and radiating light. That light, which has traveled across unimaginable distances, carries within it a unique signature, a spectrum, broken into bands of color, interspersed with dark lines that tell us what elements exist within the star. But these spectral lines are not merely static fingerprints. They are dynamic, changing in subtle ways depending on the star's magnetic environment. It is here, in the hidden realms of magnetism, that the true complexity of stellar light unfolds. Magnetic fields in stars arise from deep within their interiors. They are generated by the movement of electrically charged gases, plasma, swirling through the star's convection zones. This movement creates a dynamo effect, twisting and intensifying the magnetic field. These fields then burst through the star's surface in loops and arches, interacting with the charged particles in the star's outer layers, shaping both the appearance and the behavior of the light that escapes into space. One of the most fascinating consequences of these magnetic fields is the Zeeman effect, where the magnetic field causes certain spectral lines to split into multiple components. This effect was first observed in the late 19th century by Dutch physicist Peter Zeeman, but its full importance became clear only much later when astronomers realized that these subtle splits in the spectrum were a direct indication of a star's magnetic field. Imagine for a moment a star much like our Sun. Light escapes from its surface, carrying information about the elements within it: hydrogen, helium, calcium, iron, and more. Under normal circumstances, these elements absorb light at specific wavelengths, creating dark lines in the star's spectrum. But when magnetic fields are present, they disrupt the energy levels of the atoms in the star, altering the wavelengths at which they absorb light. The result is that a single spectral line splits into several closely spaced lines, each slightly shifted from the original position. This spectral fingerprint, tells us not only about the elements present in the star, but also about the strength and orientation of the magnetic fields at work. In stars with particularly strong magnetic fields, such as sunspots on our own sun, the Zeeman effect is even more pronounced. These dark, cooler regions of the sun are threaded by intense magnetic fields, and when astronomers examine the light coming from sunspots, they see the spectral lines broadened and split, revealing the hidden power of the magnetic field below. As we move beyond our sun to study other stars, we find that magnetism plays a crucial role in their lives as well. In some stars, known as magnetic AP stars, A-type stars with peculiar chemical compositions, the magnetic field is so strong that it influences not only the spectrum but also the distribution of elements across the star's surface. These stars often show unusual abundances of certain elements, like strontium, chromium, or rare earth metals, which are concentrated in patches on the star's surface, drawn there by the magnetic forces at play. These fields are not static, either. They evolve over time, driven by the star's internal dynamics. As the star rotates, its magnetic field twists and winds, sometimes snapping like a taut rubber band and releasing bursts of energy in the form of stellar flares. These flares, much like the solar flares we observe on the sun, eject massive amounts of charged particles into space, interacting with the star's light and altering its spectrum in brief but dramatic ways. In the most extreme cases, magnetic fields can give rise to some of the universe's most enigmatic objects, magnetars. These highly magnetized neutron stars possess magnetic fields 1,000 trillion times stronger than Earth's. In these stars, the magnetic field is so intense that it can distort atoms into elongated shapes, twisting the very fabric of matter itself. The spectra of magnetars are unlike anything else in the cosmos, as their light is constantly warped by the overwhelming magnetic forces. The Zeeman effect here becomes a violent stretching of spectral lines, a reflection of the unimaginable power contained within these stars. But magnetic fields do more than just alter the light we observe. They also drive the life cycles of stars. In young, rapidly rotating stars, the magnetic field can act like a cosmic brake, slowing the star's rotation over millions of years. These stars spin faster and generate more intense magnetic activity, often resulting in powerful flares and winds that strip away outer layers of gas and dust. Over time, as the star's rotation slows, its magnetic field weakens, and the flares become less frequent, allowing the star to settle into a quieter phase of its life. Even in the later stages of stellar evolution, magnetic fields continue to shape the fates of stars. As a star exhausts its nuclear fuel and begins to shed its outer layers, magnetic fields can sculpt these outflows into intricate structures, forming planetary nebulae, glowing shells of gas that expand outward, illuminated by the dying star at their center. The magnetic field, twisting and turning, molds these nebulae into spirals, hourglass shapes, and other stunning forms that grace the cosmos like cosmic artworks. Magnetism is, in many ways, the silent architect of stellar life. It governs the surface features of stars, it shapes their spectra, and it even dictates the pace of their evolution. By studying the magnetic fields of stars, we learn not only about the stars themselves but also about the fundamental forces that govern the universe. As we continue to gaze at the heavens, analyzing the light from distant stars, we are reminded that the universe is not just a place of calm order and beauty. It is a place of dynamic, ever-changing forces, where invisible magnetic fields twist and turn, subtly influencing the light that journeys across the void. Every star, in its spectrum, carries with it a message from the cosmos, a message written not just in the language of light, but in the hidden dialect of magnetism. In this way, the stars are more than mere points of light in the night sky. They are beacons of knowledge, revealing to us the deep and intricate workings of the universe. By studying the magnetic fields that shape their spectra, we glimpse the invisible forces that govern not only the stars themselves but also the very structure of the cosmos. The profound influence of magnetic fields on the spectra of stars is not merely a scientific curiosity. It is a key to unlocking some of the most elusive mysteries of the universe. These invisible forces, woven into the very fabric of stars, are a reminder that the cosmos is far more dynamic and unpredictable than it first appears. With each discovery about the role of magnetic fields, we inch closer to understanding the deeper mechanics of stellar evolution, star formation, and even the broader forces shaping galaxies. To truly grasp the influence of magnetic fields on starlight, we must first appreciate the complexity of stars themselves. Stars are not static objects. They are living, breathing entities, in constant flux as they fuse elements in their cores and release energy into the cosmos. This energy, carried outward as light, emerges from the star's surface, bringing with it an imprint of the processes happening within. But as the light travels through the star's magnetic field, it is bent, twisted, and reshaped, carrying with it evidence of the unseen forces that govern the star's behavior. The stellar dynamo and magnetic chaos. Deep within the core of a star, nuclear fusion powers everything, but it is the outer layers, the convection zone, that give rise to magnetic fields. Here, hot plasma churns and rises, creating a dynamo effect as charged particles flow in complex patterns. These motions generate magnetic fields that twist and intensify as they move toward the star's surface. Over time, these magnetic fields create a chaotic, ever-changing environment on the star's surface, where sunspots, flares, and massive eruptions of plasma, known as coronal mass ejections, are all tied to the magnetic forces at work. One of the clearest ways we observe this magnetic chaos is through starspots. The stellar equivalent of the sunspots we see on our sun. Starspots are cooler, darker regions on a star's surface where magnetic fields have suppressed the flow of hot plasma from below. When astronomers study the spectra of stars with prominent starspots, they often observe changes in the spectral lines, broadening, splitting, or shifting, caused by the intense magnetic fields in these regions. This phenomenon gives us direct insight into the strength of a star's magnetic field and the turbulent forces reshaping its surface. In stars much larger and hotter than our Sun, such as O-type and B-type stars, the magnetic fields can be even more extreme. These stars are young, massive, and incredibly energetic, with powerful magnetic fields that extend far beyond the star's surface. The light emerging from these stars is often polarized, meaning the magnetic fields have altered the orientation of the light waves themselves. By studying this polarization, astronomers can map the structure of the magnetic fields around these stars, revealing intricate webs of magnetic loops, arches, and spirals. In particular, magnetic AP stars, a subgroup of A-type stars, exhibit some of the most pronounced magnetic field effects in their spectra. These stars often show unusually strong magnetic fields that are stable and highly structured, sometimes organized into dipoles or quadrupoles, similar to Earth's magnetic field but on a much larger scale. The spectra of AP stars show dramatic splitting of lines, especially those of certain elements like silicon, chromium, and strontium, which are drawn into specific regions of the star's magnetic field. These stars act as natural laboratories, helping astronomers understand how magnetic fields can trap and organize matter on a stellar scale. Magnetic fields and stellar winds. Beyond the surface of stars, magnetic fields also shape the flow of matter outward into space. Stars constantly lose mass through stellar winds, streams of charged particles that escape the star's gravitational pull and flow into the surrounding space. In stars like the Sun, these winds are relatively gentle, but in more massive stars, the winds can be incredibly powerful, ejecting vast amounts of material at speeds of millions of kilometers per hour. Magnetic fields play a crucial role in shaping these stellar winds. In stars with strong magnetic fields, the winds are often channeled along magnetic field lines, creating streams of material that spiral outward in complex patterns. These winds can carry away significant portions of a star's mass over time, altering its evolution and even influencing the formation of planetary systems around it. For stars nearing the end of their lives, magnetic fields can have even more dramatic effects. As a star begins to shed its outer layers in the form of a planetary nebula, the magnetic field shapes the outflowing gas into intricate structures, spirals, rings, and hourglass shapes. These nebulae, often illuminated by the dying star at their center, are among the most beautiful and enigmatic objects in the cosmos. The magnetic field, though invisible, leaves its unmistakable mark on the shape and movement of the gas, sculpting the nebula into forms that reveal the star's final, turbulent breaths. magnetic monsters, neutron stars, and magnetars. In the most extreme cases, magnetic fields give rise to some of the universe's most bizarre and powerful objects: neutron stars and magnetars. These stellar remnants are born from the collapse of massive stars, their cores compressed into incredibly dense objects only a few kilometers in diameter. The magnetic fields of neutron stars are unimaginably strong, trillions of times more powerful than Earth's magnetic field, and they have a profound effect on the light and matter around them. A neutron star's magnetic field is so intense that it distorts spacetime itself, bending light and warping the space around the star. As the neutron star spins, its magnetic field interacts with the charged particles in its environment, creating beams of radiation that sweep across space like cosmic lighthouses. These are the pulsars, neutron stars that emit regular pulses of light as they rotate, their beams flashing past Earth like a cosmic beacon. But the most extreme examples are magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. These magnetic fields are so powerful that they can tear apart atoms, distorting the very structure of matter. The spectra of magnetars are radically different from those of other stars, showing shifts and distortions caused by the overwhelming magnetic forces. In some cases, magnetars release bursts of high-energy radiation, known as soft gamma-ray bursts, which can briefly outshine entire galaxies. The magnetic fields of magnetars also twist and warp the star's surface, causing it to crack and release massive amounts of energy in the form of starquakes. These violent events send shockwaves through space, producing flares of radiation that are detectable across vast distances. Magnetars represent the ultimate manifestation of the power of magnetic fields in shaping the behavior of stars and the light they emit. Magnetic fields and planetary systems. The influence of stellar magnetic fields extends far beyond the stars themselves, reaching into the planetary systems that form around them. In young stars, strong magnetic fields can interact with the protoplanetary disks of gas and dust that surround them, shaping the orbits and growth of planets. Magnetic fields can carve gaps in these disks, directing the flow of material and determining where planets can form. They can also influence the rotation of young planets, slowing them down or speeding them up, depending on the orientation of the magnetic field. For planets orbiting close to their parent stars, the stellar magnetic field can have a profound impact on the atmosphere. Planets like hot Jupiters, which orbit very close to their stars, are bombarded by intense stellar winds and magnetic activity, often stripping away their outer layers. In some cases, the magnetic field of the star can create spectacular auroras in the planet's atmosphere, similar to the northern lights on Earth but on a far grander scale. Even for more distant planets, like those in the habitable zones of stars, the magnetic field plays a protective role. Just as Earth's magnetic field shields us from the harmful effects of solar wind, the magnetic fields of other planets can protect their atmospheres from being eroded by stellar winds. Without this protection, a planet's atmosphere could be stripped away, leaving it barren and lifeless. The cosmic web of magnetism. Ultimately, the story of magnetic fields and the spectra of stars is part of a much larger cosmic web of forces. Magnetism is not confined to individual stars. It permeates galaxies, threading through the vast interstellar spaces that separate stars and planets. It shapes the formation of galaxies, drives the evolution of stellar clusters, and influences the movements of gas and dust throughout the universe. In many ways, magnetic fields are the invisible architects of the cosmos. Though they cannot be seen directly, their effects are visible in the light of stars, in the shapes of nebulae, and in the structure of entire galaxies. Through the study of stellar spectra, we gain a window into this hidden world of forces, unlocking the secrets of magnetism that govern the universe at every scale. As we continue to explore the universe, we are reminded that the stars are not just isolated points of light. They are part of a vast, interconnected web of energy and magnetism, shaping the cosmos in ways both seen and unseen. The spectra of stars are not merely the fingerprints of distant worlds. They are the echoes of the invisible forces that guide the universe's dance. The magnetic fields of stars are among the most elusive and powerful forces shaping the cosmos, and as we unravel their mysteries, we come to realize how integral they are to the structure of not just individual stars but entire galaxies. In every stellar spectrum, we find the signature of these invisible fields, imprinting themselves on the light that reaches us across the void. To truly understand the influence of magnetic fields on the spectra of stars, we must zoom out and see how these forces operate on both the smallest and grandest scales of the universe. A galactic dance of magnetism. At the heart of every galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational behemoth around which stars, gas, and dust swirl in a delicate balance. But what often goes unnoticed is the role magnetic fields play in this cosmic ballet. Galaxies themselves are threaded with magnetic fields that influence the movement of stars and the interstellar medium, those vast clouds of gas and dust that exist between the stars. These fields stretch across thousands of light-years, subtly guiding the formation of stars, the collapse of molecular clouds, and even the flow of entire galactic arms. The magnetic fields of galaxies are not uniform. They twist and spiral, much like the galaxies themselves. As the galaxy rotates, so too do its magnetic fields, creating enormous loops and filaments that channel the flow of gas and dust. These fields are detected through synchrotron radiation, a type of light emitted when charged particles spiral along magnetic field lines at near-light speeds. This radiation gives us a glimpse into the hidden structure of a galaxy's magnetic field, revealing the vast, interconnected webs of magnetism that crisscross the stars and shape their formation. When astronomers study the light from distant galaxies, they find evidence of these fields in the way starlight is polarized. The magnetic fields twist and warp the light as it travels through space, creating subtle signatures in the galaxy's spectrum. These signatures tell us about the strength and orientation of the magnetic fields, offering clues about how galaxies evolve and how stars form within them. Star formation and magnetic cradles. Stars are born in the cold, dark regions of space, in vast clouds of gas and dust known as molecular clouds. These clouds are the stellar nurseries of the universe, where the raw materials of stars gather and eventually collapse under their own gravity to form new stars. But the process of star formation is not a simple one. Magnetic fields play a crucial role in shaping the fate of these clouds and determining how, when, and where stars form. As a molecular cloud collapses, the gas and dust begin to clump together, forming dense regions known as protostars. But the collapse of the cloud is resisted by its internal magnetic field. This magnetic field acts like a cosmic scaffold, slowing down the collapse and redistributing the energy within the cloud. In some cases, the magnetic field can even halt the collapse entirely, creating a delicate balance between gravity and magnetism. As the protostar grows, its magnetic field becomes more organized, aligning with the flow of gas into the forming star. These magnetic fields channel material onto the growing protostar in spiraling jets and outflows, creating spectacular displays of light and matter. These jets are visible as beams of glowing gas, ejected from the poles of the protostar at high speeds, carrying away excess angular momentum and allowing the star to grow in size. When astronomers study the spectra of young stars and their surrounding disks, they often see the effects of these magnetic fields in the form of Doppler shifts, changes in the wavelengths of light caused by the motion of material moving along magnetic field lines. These shifts give astronomers insight into the speed and direction of the jets, allowing them to map the magnetic fields that shape the birth of new stars. Without magnetic fields, the process of star formation would be far more chaotic, with stars collapsing too quickly or forming in random, uncontrolled bursts. The presence of magnetism creates a natural order, a cosmic regulator that ensures stars form at the right pace, with the right amount of material, and in the right locations. Magnetic fields and stellar evolution. As stars evolve, their magnetic fields continue to influence every aspect of their lives. In middle-aged stars like our Sun, the magnetic field helps to drive cycles of activity, including the appearance of sunspots, solar flares, and coronal mass ejections. These cycles are not random but follow an 11-year pattern known as the solar cycle, during which the Sun's magnetic field flips, reversing its polarity. This magnetic flip causes changes in the number of sunspots, the intensity of solar winds, and the overall behavior of the star. When astronomers study the spectra of stars like the Sun, they observe changes in the spectral lines over time, corresponding to the star's magnetic activity. During periods of high magnetic activity, the lines in the star's spectrum become more broadened and distorted as the magnetic field affects the movement of gas in the star's atmosphere. This broadening tells us not only about the star's magnetic field but also about the energy being released in the form of stellar winds and flares. For massive stars, magnetic fields play an even more dramatic role in their evolution. As these stars approach the end of their lives, their magnetic fields become tangled and intensified. This can lead to the formation of magnetic bubbles, regions of space filled with charged particles and magnetic fields that are ejected from the star's surface. These bubbles expand outward, creating beautiful and complex shapes in the star's surrounding nebula. In the final stages of a star's life, when it collapses to form a white dwarf, neutron star, or black hole, its magnetic field is compressed along with the star itself. This compression intensifies the magnetic field, sometimes by orders of magnitude, creating some of the strongest magnetic fields in the universe. In the case of neutron stars and magnetars, these magnetic fields are so intense that they warp space and time, bending light and distorting the very atoms in their vicinity. Magnetic fields also influence the way stars die. For example, in stars that end their lives in supernova explosions, the magnetic field plays a key role in shaping the explosion and determining the distribution of material ejected into space. The magnetic field can twist and contort the star's outer layers, creating jets of material that shoot out at high speeds, forming the characteristic shapes of supernova remnants. The cosmic impact of stellar magnetism. The influence of magnetic fields does not end with the stars themselves. These invisible forces extend far into space, affecting the environment around the star and even influencing the development of life on planets like Earth. The solar wind, a stream of charged particles carried by the sun's magnetic field, interacts with Earth's own magnetic field, creating the magnetosphere, a protective bubble that shields the planet from harmful cosmic radiation. Without Earth's magnetic field, life as we know it might never have developed. The magnetic field deflects most of the charged particles from the solar wind, preventing them from stripping away our atmosphere and exposing the surface to intense radiation. On planets without strong magnetic fields, such as Mars, the solar wind has eroded the atmosphere over time, leaving the planet barren and exposed. The interaction between a star's magnetic field and its planets can also give rise to stunning displays of light known as auroras. On Earth, these are the northern and southern lights, caused when particles from the solar wind collide with the atmosphere, creating beautiful curtains of green, blue, and red light. Similar auroras have been observed on other planets in our solar system, such as Jupiter and Saturn, where the interaction between the planet's magnetic field and the solar wind creates dazzling light shows. In exoplanetary systems, those orbiting stars other than our Sun, the presence or absence of magnetic fields could be a key factor in determining whether a planet is habitable. Planets that orbit too close to their parent star, like the hot Jupiters mentioned earlier, are bombarded by intense magnetic activity, which can strip away their atmospheres and make them inhospitable to life. On the other hand, planets with strong magnetic fields may be better protected, allowing them to retain their atmospheres and develop the conditions necessary for life. The future of stellar magnetism research. As our understanding of stellar magnetism deepens, so too does our ability to detect and study these invisible fields. New technologies, such as space telescopes equipped with polarimeters, instruments designed to measure the polarization of light, are allowing astronomers to map the magnetic fields of distant stars in unprecedented detail. By studying the polarization of starlight, we can trace the magnetic field lines that surround stars and their planets, unlocking new insights into how these fields shape the evolution of stars, planetary systems, and even galaxies. In the coming decades, missions like the James Webb Space Telescope and next-generation observatories will provide even more detailed spectra of distant stars, allowing us to probe their magnetic fields with greater precision. These observations will help answer some of the most fundamental questions about the role of magnetism in star formation, stellar evolution, and the fate of planetary systems. A universe shaped by magnetism. In the end, the story of magnetic fields and the spectra of stars is one of cosmic connection. From the smallest molecular cloud to the largest galaxy, magnetic fields weave through the universe, shaping the formation of stars, guiding the flow of gas and dust, and influencing the development of life itself. They are the invisible architects of the cosmos, sculpting the universe in ways that we are only just beginning to understand. Every time we look at a star's spectrum, we are seeing the hidden hand of magnetism at work. The subtle shifts and splits in the light tell us not only about the star's chemical composition but also about the forces that shape its life and death. A galactic dance of magnetism. As we delve deeper into the influence of magnetic fields on a galactic scale, it becomes clear that magnetism is not confined to individual stars or planetary systems. Instead, it plays a crucial role in shaping entire galaxies and even the intergalactic medium that spans the vast distances between galaxies. Magnetic fields permeate the cosmos, guiding the movement of gas and dust, influencing star formation, and possibly playing a role in the evolution of galaxies themselves. In this dance of magnetism, we begin to see how interconnected all aspects of the universe truly are, from the smallest particles to the grandest structures. Galactic magnetic fields, the cosmic web. Within the heart of every galaxy, magnetic fields thread through the stars, gas clouds, and dust, creating a cosmic web of invisible forces. These galactic magnetic fields are not uniform but instead form intricate patterns, stretching across the spiral arms of galaxies and often following the curvature of the galaxy itself. Much like the magnetic fields of individual stars, galactic fields are generated by the movement of charged particles, plasma, within the galaxy's rotating disk. In spiral galaxies like our own Milky Way, these magnetic fields are most intense along the spiral arms, where star formation is actively occurring. The swirling motion of the galaxy acts like a vast dynamo, winding up the magnetic field lines and amplifying their strength. The result is a magnetic field that wraps around the galaxy like a coiled spring, with field lines following the path of the spiral arms. These fields can extend for thousands of light years, influencing the movement of gas and dust across vast distances. The interstellar medium, ISM, the space between stars, contains vast clouds of gas and dust, much of which is ionized and thus responsive to magnetic forces. As gas clouds move through the galaxy, they interact with the magnetic field, causing them to compress, twist, and fold. This interaction is crucial for the process of star formation. Magnetic fields can both help and hinder the collapse of these clouds, determining where stars form and how quickly they evolve. In regions where the magnetic field is particularly strong, it can slow down the collapse of gas clouds, allowing for the formation of massive, long-lived stars. The presence of magnetic fields also influences the galactic winds, streams of charged particles that are blown out of the galaxy by supernova explosions and intense stellar activity. These winds, guided by magnetic fields, help regulate the flow of material into and out of the galaxy, playing a key role in the galaxy's overall structure and evolution. The magnetic fields act as cosmic barriers, slowing down or redirecting the movement of these winds, creating regions of turbulence and calm within the galaxy. Synchrotron radiation, the signature of galactic fields. One of the most striking manifestations of magnetic fields on a galactic scale is synchrotron radiation, a type of light emitted when charged particles, such as electrons, spiral along magnetic field lines at near-light speeds. This radiation is particularly important for astronomers because it reveals the structure and strength of magnetic fields in galaxies and the interstellar medium. Synchrotron radiation is most commonly observed in radio wavelengths, making radio telescopes invaluable tools for studying magnetic fields in space. When astronomers observe a galaxy in radio light, they often see diffuse, glowing halos around the galaxy's disk. These halos are the result of synchrotron radiation emitted by electrons moving along the galactic magnetic field. By mapping this radiation, astronomers can trace the shape and strength of the magnetic field across the entire galaxy, revealing the intricate patterns of magnetism that thread through the stars and gas. In many galaxies, synchrotron radiation reveals the presence of magnetic loops and filaments, structures that extend for thousands of light years. These loops are thought to form when magnetic fields become tangled and stretched by the galaxy's rotation, creating regions of intense magnetic activity. In some cases, these magnetic loops can trap and accelerate particles to near-light speeds, creating jets of radiation that extend far beyond the galaxy's disk. One of the most dramatic examples of synchrotron radiation occurs in active galactic nuclei (AGN), the extremely energetic regions at the centers of some galaxies where a supermassive black hole resides. In AGN, the black hole's magnetic field interacts with the surrounding gas and dust, creating powerful jets of charged particles that shoot out from the galaxy's core. These jets emit intense synchrotron radiation, which can be detected by radio telescopes from millions or even billions of light-years away. The jets are guided by the magnetic field, creating long, narrow beams of radiation that extend far beyond the galaxy's core, sometimes stretching for thousands of light-years into intergalactic space. The role of magnetic fields in star formation. The formation of stars within a galaxy is a delicate process, one that is intricately influenced by the presence of magnetic fields. In regions of active star formation, such as the spiral arms of the Milky Way, magnetic fields act as both catalysts and regulators of the birth of stars. Stars are born from the collapse of molecular clouds, vast regions of cold gas and dust that are scattered throughout the galaxy. As these clouds collapse under the force of gravity, magnetic fields within the cloud act as a stabilizing force, resisting the collapse and slowing down the process. In many cases, the magnetic field channels the collapsing material into specific regions, creating filaments and dense cores where stars will eventually form. This process is known as magnetic fragmentation, where the magnetic field creates pockets of density within the molecular cloud. These dense regions are where stars are most likely to form, but the magnetic field also plays a role in determining the size and mass of the stars that emerge. Strong magnetic fields tend to produce smaller, less massive stars, as the field prevents too much material from collapsing into a single core. In contrast, weaker magnetic fields allow for the formation of more massive stars. As the stars begin to form, the magnetic field continues to shape their evolution. The young stars, still embedded within the molecular cloud, are often surrounded by accretion disks of gas and dust that feed material onto the growing star. The magnetic field threads through these disks, creating jets of material that shoot out from the star's poles, carrying away excess angular momentum and allowing the star to grow more efficiently. These jets, guided by the magnetic field, create spectacular outflows of gas that are visible in both optical and radio light. Magnetic fields and the galactic dynamo. One of the most intriguing questions in astrophysics is how galactic magnetic fields are sustained over billions of years. Galaxies are not static objects. They rotate, evolve, and interact with other galaxies. Yet their magnetic fields remain intact and often grow stronger over time. This persistence is thought to be the result of a process known as the galactic dynamo. The galactic dynamo is similar to the dynamo process that generates magnetic fields in stars. It relies on the rotation of the galaxy and the movement of charged particles within its disk to generate and amplify magnetic fields. As the galaxy rotates, charged particles in the interstellar medium move in complex patterns, creating electric currents that generate magnetic fields. These fields are then stretched, twisted, and amplified by the galaxy's rotation, creating the large-scale magnetic fields that we observe today. Over time, the dynamo process can convert kinetic energy from the galaxy's rotation into magnetic energy, sustaining the magnetic field for billions of years. In some cases, the magnetic field can even grow stronger over time as the galaxy continues to rotate and evolve. This process is not fully understood, but it is thought to be a key mechanism for maintaining the magnetic fields of spiral galaxies like the Milky Way. Magnetic fields and galactic evolution. The magnetic fields of galaxies are not just passive structures. They actively influence the evolution of the galaxy itself. In regions of intense magnetic activity, the field can shape the flow of gas and dust, influencing the formation of stars and the growth of stellar clusters. In some cases, magnetic fields can even trigger the formation of new stars by compressing gas clouds and initiating the collapse process. Magnetic fields also play a role in regulating the movement of gas between the galaxy and the intergalactic medium. The galactic wind streams of charged particles that flow out of the galaxy are often guided by magnetic fields, creating funnels of gas that extend far beyond the galaxy's disk. These winds carry away gas and dust, slowing down the rate of star formation and influencing the overall structure of the galaxy. In galaxies with active black holes at their cores, magnetic fields play a crucial role in shaping the jets of material that are ejected from the black hole's surroundings. These jets, guided by the magnetic field, can have a profound impact on the galaxy, heating up the surrounding gas and preventing it from collapsing to form new stars. This process, known as feedback, is thought to be a key mechanism for regulating star formation in galaxies, preventing them from growing too quickly and becoming unstable. A universe of interconnected forces. The magnetic fields of galaxies are not isolated phenomena. They are part of a larger cosmic web of magnetism that extends across the universe. As galaxies interact with one another, through collisions, mergers, or gravitational encounters, their magnetic fields become entangled, creating complex structures that span vast distances. These magnetic interactions can trigger bursts of star formation, create shock waves that ripple through the intergalactic medium, and even influence the formation of galaxy clusters. In the intergalactic medium, IGM, the space between galaxies' magnetic fields are thought to play a key role in the movement of gas and the formation of large-scale structures. The IGM contains vast amounts of diffuse gas, much of which is ionized and therefore responsive to magnetic forces. As gas moves through the IGM, it interacts with magnetic fields, creating shock waves and turbulence that influence the formation of galaxies and clusters of galaxies. The role of magnetic fields in star formation. Star formation is one of the most fundamental processes in the universe, responsible for creating the celestial bodies that light up galaxies and give rise to planetary systems. While gravity is the primary force driving the collapse of molecular clouds, the dense regions of gas and dust where stars are born, magnetic fields play a crucial and often underappreciated role in guiding, regulating, and sometimes even resisting this process. These invisible magnetic threads stretch across vast distances, influencing how gas collapses into stars, how those stars grow, and how entire star clusters emerge from the interstellar medium. Molecular clouds, the stellar nurseries. Stars form within molecular clouds, enormous, cold regions of gas and dust that are scattered throughout galaxies. These clouds are dense enough to prevent ultraviolet light from nearby stars from breaking apart molecular bonds, allowing gases like hydrogen to exist in molecular form, hence their name. However, molecular clouds are also highly magnetized. The gas within them is partially ionized, meaning it contains free electrons and protons that respond to magnetic fields. These magnetic fields thread through the cloud like an invisible web, influencing the behavior of the gas and dust within. As a molecular cloud begins to collapse under its own gravity, magnetic fields act as a stabilizing force. In regions where the magnetic field is strong, it can support the cloud against gravity, slowing down or even preventing the collapse. The presence of these magnetic fields creates a delicate balance between gravitational forces, which seek to pull the cloud inward, and magnetic forces, which resist that collapse. The strength of the magnetic field in a molecular cloud determines how quickly or slowly star formation occurs. In clouds with strong magnetic fields, the collapse is slower, resulting in fewer stars forming over longer periods. In contrast, in clouds with weaker magnetic fields, gravity dominates, leading to a more rapid and chaotic collapse, producing many stars in a shorter amount of time. This interplay between gravity and magnetism helps to regulate the rate of star formation across galaxies, ensuring that stars form at a pace that allows for the long-term stability of the galaxy. Magnetic fragmentation, sculpting the stellar landscape. As the molecular cloud collapses, magnetic fields influence how the gas fragments into smaller clumps, each of which will eventually form a star or a group of stars. This process is known as magnetic fragmentation, and it plays a critical role in determining the distribution of star masses within a star-forming region. In regions where the magnetic field is strong, the cloud fragments into smaller, less massive clumps, as the field lines resist the free collapse of gas. These clumps tend to form lower-mass stars, which live longer and burn their fuel more slowly. On the other hand, in regions where the magnetic field is weaker, the cloud fragments into larger clumps that collapse more easily, forming more massive stars. These massive stars burn brightly but live shorter lives, eventually exploding as supernovae and seeding the interstellar medium with heavy elements. This magnetic fragmentation process helps explain the initial mass function, IMF, a statistical distribution that describes the range of star masses produced in any given star-forming region. Magnetic fields influence the IMF by controlling the size and mass of the gas clumps from which stars form. The balance between magnetic forces, gravity, and turbulence in the molecular cloud ultimately determines how many low-mass versus high-mass stars are produced, shaping the overall structure of the galaxy's stellar population. The formation of protostars, magnetic funnels, and jets. As the molecular cloud collapses and fragments, the individual clumps of gas that will become stars, known as protostars, begin to form. These protostars are surrounded by disks of gas and dust, called accretion disks, which feed material onto the growing star. But the collapse of a gas cloud is not a simple, orderly process. As the protostar forms, it spins faster due to the conservation of angular momentum, creating a centrifugal force that would normally prevent further accretion of material. This is where magnetic fields come into play. The magnetic fields threading through the protostar and its surrounding disk create magnetic funnels, channels along which gas and dust are funneled toward the protostar's poles. These magnetic funnels help direct material onto the protostar, allowing it to continue growing even as it spins. Without this magnetic regulation, the protostar would quickly stop accreting material, limiting its growth and leading to a much smaller final star. In addition to these magnetic funnels, the protostar generates powerful magnetic jets, beams of material that shoot out from its poles at high speeds. These jets are formed when the magnetic field lines around the protostar are twisted by the star's rotation, creating tension that eventually snaps, releasing energy and accelerating gas along the magnetic field lines. The jets carry away excess angular momentum from the protostar, allowing it to continue accreting material without spinning too fast and breaking apart. These jets can extend for light years, and their presence is often one of the first visible signs that a new star is forming. These jets and outflows are not just impressive displays of stellar birth. They also play a crucial role in regulating the growth of the star. By ejecting material along the magnetic field lines, the protostar sheds excess mass and energy, ensuring that it doesn't collapse too quickly or grow too large too fast. In this way, magnetic fields help to create a balance between the forces that drive star formation and the forces that resist it. Magnetic braking, slowing the spin of stars. One of the most intriguing effects of magnetic fields in star formation is a process known as magnetic braking, where the magnetic field acts to slow down the rotation of a forming star. When a molecular cloud collapses to form a star, the material in the cloud starts to spin faster, much like an ice skater pulling in their arms to spin more quickly. If left unchecked, this rapid spin would cause the star to break apart before it could fully form. Magnetic braking provides the solution to this problem. As the star forms, its magnetic field extends outward, connecting with the surrounding gas and dust in the molecular cloud. This magnetic connection creates a torque, or twisting force, that transfers angular momentum from the star to the surrounding material. In effect, the magnetic field acts like a brake, slowing down the star's rotation and allowing it to maintain its structural integrity. This process is crucial for the formation of stable stars, as it prevents them from spinning out of control during their early stages of development. Magnetic braking continues to influence stars long after they have fully formed. In young stars, the magnetic field interacts with the star's stellar wind, a stream of charged particles that flows away from the star. As the stellar wind escapes into space, it drags the magnetic field with it, carrying away angular momentum and slowly reducing the star's rotation over time. This is why older stars, like our Sun, tend to rotate more slowly than younger, more active stars. The role of magnetic fields in massive star formation. While magnetic fields are important for all types of star formation, they play an especially critical role in the formation of massive stars, those that are more than 8 times the mass of the Sun. Massive stars are rare, but they have an outsized impact on their surrounding environment due to their intense radiation and powerful stellar winds. In massive star-forming regions, the magnetic field is often strong enough to significantly slow down the collapse of gas and dust, allowing only the densest, most massive clumps to form stars. The presence of a strong magnetic field also influences the structure of the resulting star. Massive stars tend to form in highly magnetized regions, where the magnetic field helps to stabilize the gas and prevent it from fragmenting into smaller clumps. This results in the formation of fewer, but more massive stars. Once a massive star forms, its magnetic field continues to shape its evolution. The intense radiation and stellar winds produced by a massive star interact with the magnetic field, creating shock waves and turbulence in the surrounding gas. These interactions can trigger the formation of new stars in nearby regions by compressing gas and dust and setting off a chain reaction of star formation. In this way, massive stars act as cosmic engines, using their magnetic fields to influence the birth of new generations of stars. The influence of magnetic fields on star clusters. Star formation rarely occurs in isolation. Most stars are born in groups, known as star clusters, where hundreds or even thousands of stars form from the same molecular cloud. Magnetic fields play a key role in shaping the structure and dynamics of these clusters, influencing how stars form, how they interact with each other, and how the cluster evolves over time. In star clusters, the magnetic field helps to regulate the distribution of stars by influencing the motion of gas and dust within the cluster. As stars form, their individual magnetic fields interact with the larger magnetic field of the cluster, creating complex patterns of motion. These interactions can lead to the formation of subclusters, smaller groups of stars within the larger cluster, that eventually merge to form a single cohesive cluster. Magnetic fields also help to prevent the cluster from dispersing too quickly. As stars form, they release energy in the form of radiation and stellar winds, which can push gas and dust out of the cluster and cause it to lose mass. However, the magnetic field helps to hold the cluster together by creating a magnetic cushion that resists the outward flow of material. This allows the cluster to remain intact long enough for stars to continue forming and interacting with each other. The future of magnetic fields in star formation research. As our understanding of star formation deepens, the role of magnetic fields is becoming increasingly central to the story. New observational techniques, such as high-resolution radio and infrared telescopes, are allowing astronomers to map the magnetic fields in molecular clouds and star-forming regions with unprecedented detail. Magnetic braking, slowing the spin of stars, continued. The phenomenon of magnetic braking is one of the most fascinating and crucial aspects of stellar evolution, particularly in the early stages of star formation. Without the process of magnetic braking, stars would rotate much more quickly than they do, potentially causing catastrophic instabilities. Magnetic braking serves as a cosmic regulator, preventing stars from spinning too rapidly as they collapse from clouds of gas and dust into fully formed stellar objects. This mechanism has a profound influence on the formation of stars, the evolution of their rotation rates over time, and their long-term stability. The origins of rapid stellar rotation. When a molecular cloud collapses to form a star, the conservation of angular momentum comes into play. Angular momentum is a fundamental property of rotating objects, and as the size of a rotating body decreases, its rotation speed must increase to conserve angular momentum. This is the same principle behind why a figure skater spins faster when they pull their arms inward. In the context of star formation, as the large molecular cloud condenses into a much smaller protostar, the rotation rate should theoretically increase dramatically. If left unchecked, this increasing rotation could become a major problem. Stars that spin too quickly are at risk of becoming unstable, with their centrifugal force potentially tearing them apart before they can reach a stable configuration. In the early stages of star formation, the rotational speeds of forming stars are often so fast that their centrifugal force would exceed the gravitational pull trying to hold the star together. Without a mechanism to slow down this rapid rotation, stars would not be able to form in a stable way. Magnetic fields as rotational brakes. Magnetic braking provides the solution to this problem. As a protostar forms, it inherits the magnetic field of the surrounding molecular cloud. This magnetic field, combined with the ionized plasma in the protostar's environment, creates a connection between the protostar and its surrounding gas and dust. As the protostar spins, it drags its magnetic field along with it. This magnetic field, in turn, is anchored in the surrounding disk of gas and dust. As the protostar continues to rotate, the magnetic field lines connecting the star to the disk become twisted and stretched. This tension in the magnetic field lines creates a braking effect, transferring angular momentum from the rapidly rotating protostar to the slower-moving surrounding material. Essentially, the magnetic field acts as a bridge, allowing the protostar to dump its excess rotational energy into the disk. Over time, this magnetic braking process slows down the rotation of the protostar, allowing it to reach a more stable state. The rate of spin decreases enough to prevent the star from tearing itself apart, ensuring that it can continue to grow by accreting material from the surrounding disk. Magnetic coupling, the link between star and disk. A key factor in the process of magnetic braking is magnetic coupling, the interaction between the star's magnetic field and the surrounding accretion disk. This coupling creates a magnetic link that allows the transfer of angular momentum between the two systems. In this process, the magnetic field lines are stretched outwards, and the outer parts of the accretion disk rotate more slowly than the protostar itself. As the magnetic field lines twist, they generate torques that act against the star's rotation. These torques gradually reduce the rotational speed of the protostar by transferring its angular momentum outward into the disk. The magnetic field lines can even reconnect far from the star, creating outflows or jets of material. These jets, which shoot out from the protostar's magnetic poles, carry angular momentum away from the system entirely, further slowing the protostar's rotation. These jets, which can extend for light years, are often some of the most visible and energetic phenomena in star-forming regions, signaling the presence of a young star that is actively undergoing magnetic braking. The role of stellar winds in magnetic braking. Even after a star has fully formed, magnetic braking continues to influence its rotation through the interaction between the star's magnetic field and its stellar wind. Stellar winds are streams of charged particles, plasma, that flow outward from the surface of a star. These winds are influenced by the star's magnetic field, and as they escape into space, they carry away angular momentum, further slowing down the star's rotation. The solar wind from our sun is a classic example of this process. The sun's magnetic field interacts with the solar wind, which carries charged particles away from the star at high speeds. As the particles travel along the magnetic field lines, they drag the field with them, creating a torque that gradually slows the sun's rotation. Over the lifetime of a star, this process of stellar wind-driven magnetic braking can significantly reduce its rotation rate. For example, young stars typically rotate much more quickly than older stars because they have had less time to lose angular momentum through their stellar winds. As stars age, magnetic braking continues to slow their spin, leading to the relatively slow rotation rates observed in stars like our sun, which is middle-aged. Magnetic braking and the formation of planets. Magnetic braking also plays a critical role in the formation of planetary systems. The interaction between a young star's magnetic field and its protoplanetary disk can influence the movement of material within the disk, affecting how planets form and migrate. In some cases, magnetic braking can cause the inner regions of the protoplanetary disk to lose angular momentum and collapse inward, bringing material closer to the star. This process can create migration pathways for newly formed planets, causing them to move inward toward the star. Planets that form in the outer regions of the disk may be drawn inward by these magnetic effects, potentially becoming hot Jupiters, gas giants that orbit very close to their parent stars. Conversely, magnetic braking can also help prevent planets from migrating too quickly or too close to the star. By redistributing angular momentum within the disk, magnetic fields create regions where material is held in place, allowing planets to form in stable orbits. This delicate balance between migration and stability is crucial for the formation of planetary systems that can sustain long-lived planets, including those in the habitable zone. Magnetic braking and stellar evolution. The influence of magnetic braking doesn't end when a star reaches the main sequence. Throughout a star's life, its magnetic field continues to interact with the surrounding environment, shaping the star's evolution. For stars like the Sun, magnetic braking through stellar winds leads to a gradual slowing of the star's rotation. This slowing has important consequences for the star's internal dynamics, particularly in terms of differential rotation, the phenomenon where different parts of the star rotate at different speeds. As the star's rotation slows, the differential rotation decreases, leading to changes in the star's magnetic field and activity cycle. This process is evident in stars of different ages. Young stars, like those in the Pleiades cluster, spin rapidly and exhibit strong magnetic activity, including powerful flares and star spots. As these stars age, magnetic braking causes their rotation rates to decrease, reducing their magnetic activity. By the time a star reaches middle age, like the Sun, its rotation has slowed significantly, and its magnetic activity has settled into a more regular cycle, such as the 11-year solar cycle observed on Earth. In the later stages of a star's life, magnetic braking continues to influence its evolution. As stars evolve into red giants, their outer layers expand, and their magnetic fields weaken. However, in some cases, the magnetic field can still interact with the star's stellar wind, shaping the outflow of material and creating intricate structures in the star's surrounding nebula. For some stars, magnetic braking plays a key role in their ultimate fate. In binary star systems, where two stars orbit each other closely, magnetic braking can cause the stars to lose angular momentum and spiral closer together. This can lead to dramatic events, such as mergers or supernova explosions, depending on the mass and composition of the stars involved. Magnetic braking in other stellar types. Magnetic braking is not limited to stars like the Sun. It also plays a significant role in the evolution of low-mass stars and brown dwarfs. These smaller, cooler stars often have stronger magnetic fields relative to their size, leading to more efficient magnetic braking. As a result, low-mass stars tend to spin more slowly than their more massive counterparts, and their magnetic activity lasts much longer. In brown dwarfs, objects that are too small to sustain hydrogen fusion in their cores, magnetic braking is especially important. Brown dwarfs form in much the same way as stars, collapsing from molecular clouds and acquiring rotation. However, because they lack the nuclear fusion that powers stars, their evolution is dominated by magnetic effects. Magnetic braking helps regulate the rotation of brown dwarfs, allowing them to maintain stability, even though they lack the energy generation mechanisms of full-fledged stars. The future of magnetic braking research. Our understanding of magnetic braking is constantly evolving, thanks to new observational tools and techniques. The study of magnetic fields in young stars and protostellar systems has advanced significantly with the development of polarimetry, a method that measures the polarization of light to detect magnetic fields. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the upcoming James Webb Space Telescope are providing high-resolution data on star-forming regions, allowing astronomers to map the magnetic fields in unprecedented detail. Numerical simulations of magnetic braking are also becoming more sophisticated. By modeling the interaction between magnetic fields, stellar winds, and accretion disks, scientists are gaining new insights into how magnetic braking shapes the early evolution of stars and planetary systems. These simulations are helping to answer key questions about the role of magnetic braking in the formation of stars, the regulation of their spin rates, and the development of complex planetary systems. The influence of magnetic fields on the spectra of stars reveals an intricate and profound relationship between the unseen forces of the cosmos and the light that reaches us across the vastness of space. From the Zeeman effect splitting spectral lines to the complex interactions between magnetic fields, stellar winds, and the formation of star spots, magnetic fields shape the very identity of stars. They regulate stellar rotation, control the behavior of gas and plasma in a star's atmosphere, and influence everything from star formation to the end stages of stellar evolution. Magnetic fields are the silent sculptors of the universe, weaving through the life cycles of stars and subtly altering the starlight that carries crucial information about their internal processes. By studying these invisible forces, astronomers unlock new insights into the behavior of stars, their magnetic activity, and the role magnetism plays in shaping the cosmos itself. If you enjoyed this exploration of magnetic fields and their influence on the spectra of stars, make sure to give this video a thumbs up and share it with others who love diving into the mysteries of the universe. Don't forget to subscribe to the channel and hit the notification bell so you never miss a journey through the cosmos. Thanks for watching, and I'll see you in the next one.